Okay, this question is still from Unit 1415. We're looking at Box E here, we're looking at applications, and I kind of like this question because it does a whole bunch of, it puts together a lot of concepts that we've looked at both in Unit 1415, in Unit 1213, reaching all the way back to Unit 910. Okay. So here's the question. Alvin is researching the population of Canada. This is a really exciting topic. I don't know, this is geography class or something like that. He finds data for the year 2001 and predictions for every 5 years after that, as shown below. We want to determine an algebraic model for Alvin's data and use it to make a reasonable prediction for the population of Canada in 2036. So they give us this table of data over here with number of years since 2000 and population in millions. And what they're asking us to come up with is an equation that relates P, population in millions, to the number of years since 2000, T. So those are our two variables. Where we want to start with this question is we want to draw a scatter plot of the data that they give us in the table. Okay? So that's what I'm going to do up here. You guys have the data in front of you, so just draw yourself a scatter plot of that data. So let's see, we got 131.1, so that's something like that. And it doesn't have to be incredibly accurate here. I'm going to use green for my points here. 11, 33.3. 33.4 it should be. 16, 34.4, 21, 35.4. And what's the last year we have? 26, 36.2. Okay. So you should have a graph that looks something like this. Now, before we get to making our prediction, if you were to describe this graph, would you say that it is linear or nonlinear? This is a 910 concept here. Linear or nonlinear? What do you think? Emily? She says it is linear. Why do you say it's linear, Emily? Yeah, you could draw a straight line through all of these things. And that's the next thing we want to do. We want to draw, remember that line of best fit, bracket 910? We want to draw a line of best fit to this data. So my line of best fit is going to go kind of something like that. Okay? It's not too bad. Okay? Now, as a side note, what's the other way of determining if your relationship is linear or nonlinear if you were given a table of values? What do you calculate from that table of values to figure out if it's linear or nonlinear? Somebody must remember this. Abby. The finite differences. So we could come over here and we could calculate our finite differences. Okay? And so we would start at the bottom and we would work our way up. And what we would get is 0.8, 1.0, 1.0, 1.2, 1.1. Now, how do we use the finite differences to tell us whether a relationship is linear or nonlinear? What do we look for in our finite differences? Emerson, what do we look for? If they're all the same. If they're all the same, what do we know about a relationship? Is it linear or nonlinear? It's linear if they're all the same. So are our finite differences all the same? Is our relationship linear? Okay. So our two definitions of how we figure out if a relationship is linear or not are now in conflict. Our first differences are telling us, no, it is not. The graph that we have made is telling us, yes, it is. The finite difference thing is a little bit unreliable here because our first differences aren't exactly the same, but they're pretty darn close to each other. I mean, 1.1, 1.2, 1, 1.8, they're very, very similar to each other. And what we see in our graph is we see that our points don't all lie in exactly a straight line, but they lie pretty close to a straight line. So we would probably say that this is a linear relationship, even though all of our finite differences aren't exactly the same. So now given that this is a linear relationship, we want to come up with an equation for it. And we know from all of our work in Unit 12-13 what that equation is going to look like. It's going to be the equation of a straight line, and it's going to have the form y equals mx plus b. Only we don't have y and x in this question. What are our two variables? They are t and p. So it's going to be population p equals some slope times t plus some intercept. Our job is to figure out the slope of our relationship and the y-intercept of our relationship. Okay. Our graph in this case is a little bit unreliable because the person who gave us this grid did this funny thing here where they do that little jagged line so that they can fit a bigger graph in a smaller space. That means we can't use the graph to make predictions as we'd like to. So we're going to do this entirely algebraically. We are going to calculate the slope using our slope formula, y2 minus y1 over x2 minus x1. Okay? And then from there, we're going to figure out our y-intercept. So what can we put into our slope formula? Well, we need two values of y, and we need two values of x. So let's take a look at this here. I've drawn my line of best fit that we want to find the equation for, so it sort of passes through most of these points here. I want to find some points that are on my line. So I'm looking for places where my line here crosses, the line of best fit that I do crosses these grid points here. So I could pick this point right here, okay, and maybe this point right here. Okay. So this point right here is 231. This point right here is 22, 35 and a half. Okay. Now, you might find that your line of best fit doesn't go through those two exact points, and that's okay. If you were to pick 2 points that your line of best fit does go through, you would use them to calculate the slope, and you'd get an answer that is pretty close to mine. Not exact, but pretty close. But those are the 2 points that I'm going to use here. So y2 minus y1, I'm going to take 35.5 minus 31. x2 minus x1 is going to be 22 minus 2. And what I'm going to get is, let's see, 35.5 minus 31 is going to be 4.5. And 22 minus 2 is going to be 20. And then I need to do 4.5 divided by 20. Oh, pull up my calculator here. .5 divided by 20 gives me 0.225. So that is going to be the slope of my relationship. Okay. So now I know my relationship is 0.225 t plus b. My job now is to figure out what is this y-intercept. So how am I going to figure out the y-intercept now that I know the slope? What can I put into this relationship between p and t? You guys have done this a million times in 14 Emerson's. Yeah, I can substitute in values for p and t. So I'm going to choose this point right here that I picked at the beginning. This is a value of t. This is a value of p right there. And I'm going to put them into my equation. So my p is 31. My t value here is 2. Okay. And I just stick them in here, 0.225 plus b. And now I want to solve this equation. So I'm going to multiply 0.225 times 2. That's what I got my calculator for, 0.45 plus b equals 31. And then to get my value for b, I'm going to subtract that 0.45 from both sides. Minus 0.45, minus 0.45, and I'm going to end up with b equals, well, let's see, 31 minus 0.45, 30.55. Okay. It would be if I was using the point out of the table, but I'm using this point that was on my line of best fit. Okay. If I had drawn my line of best fit so it went right through that point, I could use that point as well. Okay. And chances are using a point from the table would probably give you an answer that was close enough to the answer from using this point that it wouldn't matter too much. So it is a good bet to use points from the table as well. Good question. But if I use that point that was that I'd taken to use my slope, I can now put this all together. And my population model is p equals 0.225 t plus 30.55. Okay. That is my algebraic model for the population, or for Alvin's data. Now, the second part of the question says, use this to make a reasonable prediction for the population of Canada in 2036. Okay. In 2036. Back in Unit 910, they asked you questions like this, and what they wanted you to do then was extrapolate using the graph. So extend your line out so that this went way out to 2036, and you could just use that line of best fit. Our graph is a little bit too small to do that here, so we're going to have to use our equation. Okay? In 2036, okay, we want to sub something into this value, this algebraic model we have. So if they're giving us this date, 2036, are we going to sub that in for p, or are we going to sub that in for t? Does it represent population, or does it represent time? What do you think, Isaac? Does it represent population or time? Yeah, so we're going to sub this in for t. Now, small detail. We don't want to sub in 2036, because what our graph is giving us here is the number of years since the year 2000. So we want to sub in 2036 minus 2000, or a t-value of 36. Okay? Because it's 36 years since the year 2000. So let's sub this in. P equals 0.225 times 36 plus 30.55. And then we can just punch this stuff into the calculator. And I have to actually punch this in because 0.225 times 36, and then I add on my 30.55, and what I get is 38.65. Okay. So what does that number represent? We should write a little conclusion at the end that says what that number represents. In 2036, the population will be 38.65. Now, 38.65 what? Is it 38.65 people? What is this value of P measured in? Yeah, million people. And that's the big reason we put these concluding sentences at the end, because sometimes we have to change from this number that we got here using our equation to what it actually represents in terms of millions of people. And that's it for Unit 1450.